Welcome to the second lecture of the second week of Lent term, and so far in this chapter 4 we have learnt about the set of natural numbers, which can be thought of as a subset of the set of integers, and last time we began our discussion of the rational numbers, and so far what we have seen is the definition of rational numbers. So we first introduced this equivalence relation on the Cartesian product of the integers with the non-zero integers, and two pairs n comma d and n prime comma d prime in this set are said to be related to each other if the corresponding fractions are the same intuitively. That is, n by d is n prime by d prime. In other words, n d prime is equal to n prime d. And then the set of all rational numbers were all the equivalence classes that you get under this equivalence relation. And if you have an equivalence class which contains the pair n comma d, then we decided to simplify the notation and write this element simply as n by d, where n comma d is any pair in this set. And then we defined addition and multiplication of rational numbers. And today the plan is to first discuss the order relation in the set of rational numbers and then begin our discussion of the real numbers. We know that the set of integers can be considered as a subset of the rational numbers via this injective map, which sends an integer n to the corresponding rational number n by 1. And we have seen that this map preserves addition and multiplication, and now we'll show that it also preserves the order relation. So we'll define an order relation in Q, which is an extension of the order relation in Z. This order relation is defined like this. So suppose that you have two rational numbers R and S. Okay, so this R is an equivalence class containing an ordered pair m comma n, and we may assume that this n is strictly positive, and the reason is because last time we had seen that the ordered pair a comma b is related to the ordered pair minus a comma minus b. So even if the b is negative to begin with, by considering this new ordered pair minus a comma minus b will be positive, and it will belong to the same equivalence class because it's related to a comma b. So there is no loss of generality in assuming that this R is an equivalence class containing an ordered pair m comma n where the n is positive. And similarly, S is an equivalence class containing an ordered pair p comma q where the q is positive. And if you take any such representatives m comma n and p comma q, then using them we can decide whether R is strictly less than S or not. So R is strictly less than S if the following happens, namely, having chosen such representatives, MQ is strictly less than Pn. Now, of course, there may be many representatives in which the n is positive, and so we still have to check well-definedness, which we'll do in a moment. But right now, let's assume that this is well-defined and prove this theorem, which says that this order relation in Q is an extension of the order relation in Z, by which we mean that if you have two integers m and n, such that m is strictly less than n as integer, so this is the order relation in Z, then in fact when we put on our rational number glasses and view these integers as rational numbers, well, then the corresponding rational number is m by 1 and the corresponding rational number is n by 1, then they are in the same order. In other words, m by 1 is strictly less than n by 1 in Q, so this is the order relation in Q. Okay, so to check this, well, this 1 is already positive, so all we have to do is to check whether m times 1 is strictly less than n times 1 by this definition. And that's of course true because m times 1 is m and n times 1 is n, and of course m is strictly less than n because that's the hypothesis that these two integers are in this order. So this is true, and so this is an extension of the order relation in Z. So let us show that this order relation is well defined. Suppose that you have two rational numbers R and S, and suppose that R is strictly less than S. So that means that this R, which is an equivalence class, contains an ordered pair Mn where n is positive, and this equivalence class S contains an ordered pair Pq where the q is positive, and we know that Mq is strictly less than Pn. But suppose that we have another ordered pair m prime n prime in this equivalence class R where n prime is positive, and you have another ordered pair p prime q prime in this equivalence class S where the q prime is positive. So it better be the case that m prime q prime is also less than p prime n prime, because someone else might use these representatives from the R and S, and then of course the answer should be the same, that R is strictly less than S. So this should happen. So that's what we want to show. We want to show that if m by n is m prime by n prime is equal to R, and p by q is equal to p prime by q prime is S, where m prime, n prime, p prime, q prime are all integers, with n prime positive and q prime positive, and we know that R is strictly less than S, so that mq is less than pn, then we have to show that m prime q prime is also less than p prime n prime. Okay, so that's the task at hand. Now, since mq is strictly less than pn, and n prime and q prime are positive integers, we can multiply both sides by n prime q prime, which is also positive integer. So then you get mq times n prime q prime is strictly less than pn times n prime q prime, and we have the same order, so the order is preserved. We also know that since m by n is equal to m prime by n prime, we know that mn is related to m prime n prime, so that mn prime is equal to m prime n. And similarly, since these two are related, p comma q and p prime comma q prime, we also know that pq prime is equal to p prime q. And over here, when we have this inequality, we see this combination mn prime appearing, so that can be replaced by m prime n, and what's left is qq prime. And likewise here you see pq prime, which we know is p prime q, so if we make that replacement, what we are left with is nn prime. Okay, now this m prime q prime is what is appearing over here, and p prime n prime is what's appearing over here. And besides that, what we have over here are the factors nq, and over here also nq. So it's tempting to cancel this nq on both sides, and n and q are both positive, n and q are both positive, so it is indeed possible. So we have to justify why that's possible. Okay, so at the end of the day, I want to show that m prime q prime is less than p prime n prime. That was the task, right? So let's suppose that this is not true. Then by the trichotomy law, m prime q prime is bigger than or equal to p prime n prime. But now since n and q are positive integers, we can multiply both sides by nq, which is a positive integer, and this will be preserved. So you get m prime q prime times nq is bigger than or equal to p prime n prime times nq. Of course, if there's equality, you will get equality. And if it was a strict inequality, then since nq is a positive integer, the inequality will be preserved. But this thing is the exact opposite of this thing. And since we know that this holds, by the trichotomy law, this cannot hold. And so we have got a contradiction in this case. So this cannot hold. But by the trichotomy law, that means that m prime q prime is strictly less than p prime n prime. And that's what we wanted to show. So this shows that this relation is well defined. As an example of this order relation, let's show that the zero rational number is strictly less than the identity element with respect to multiplication, which we had seen is this 1. Now 0 is the rational number 0 by 1, that is, it's an equivalence class containing the ordered pair 0, 1. And similarly 1 is the rational number which is an equivalence class containing the ordered pair 1, 1. And we have 1 is of course positive. So to check this, all we have to do is to check that 0 times 1 is strictly less than 1 times 1. And of course that's true, because 0 times 1 is 0, 1 times 1 is 1, and we know that the integer 0 is strictly less than the integer 1. And so because of this, it follows that this rational number 0 is strictly less than this rational number 1. We will now show the trichotomy law for the order relation in the set of rationals. So the trichotomy law says that if R and S are two rational numbers, then one and exactly one of the following three statements holds. Either R is strictly less than S, or R is equal to S, or R is strictly bigger than S. So here is the proof. So suppose the rational number R is equal to m by n, so it's an equivalence class containing the ordered pair m comma n, where m and n are integers, and n we assume is strictly positive. And similarly S is an equivalence class containing the ordered pair p comma q, where p and q are integers and q is strictly positive. Now if I look at mq and np, these are integers, and by the trichotomy law for the order relation in the integers, we know that exactly one of the following three statements holds. Either mq is strictly less than pn, or mq is equal to pn, or mq is strictly bigger than pn. And we'll show that these three cases correspond exactly to these three cases. So this corresponds to this corresponds to this, and this corresponds to this. Now if mq is strictly less than pn, then by the definition of the order relation in the rational numbers, this exactly means that r is strictly less than s. Similarly, mq is strictly bigger than pn means exactly that r is strictly bigger than s. Okay, and what about the case when mq is equal to pn? Well, in that case we claim that r is equal to s. Indeed, if mq is equal to pn, then the ordered pair mn is related to the ordered pair pq. Indeed, mq is equal to np. But that means that the equivalence class containing this ordered pair, which is this rational number, is equal to the equivalence class containing this ordered pair, which is the rational number s. So you have that r is equal to s in this case. And so we have shown the trichotomy law. So far in this chapter 4, we have learned about the natural numbers, the integers, and the rational numbers. The integers were introduced because the algebraic equation m plus x is equal to n is not always solvable for a natural number x, where m and n are given natural numbers. But then viewing this equation in integers, it was possible to solve this in the set of integers. Similarly, the rational numbers were introduced because an equation of the type dx is equal to n, where d and n are integers and d is not equal to 0, is not always solvable in the set of integers for an integer x. But viewing this equation in the set of rational numbers, this is then always possible. But now with the rational numbers, it turns out that we cannot do analysis because it does not have the least upper bound property, and this is an analytical hurdle which we want to overcome, and for that reason the real numbers will be introduced. Okay, so let's recall again what this analytical hurdle is. The set of rational numbers we have seen already does not have the least upper bound property. So in lecture 1 of the Michaelmas term, if you look at the slides, and in particular the slide numbers 19, 20, or alternatively example 1.13 in the lecture notes, then we had given the following example of a subset of the set of rational numbers, which is a non-empty subset. It is bounded above, but it does not possess a least upper bound in the rational numbers. So this set was the set of all rational numbers r whose square is less than or equal to 2, and this is not empty, for example, because the rational number 1 belongs to it. We had seen that it is bounded above by 2, but we had shown that if u star is the least upper bound of s, then u star has got to satisfy u star square is equal to 2, and we know that there is no rational number whose square is equal to 2. So this set of rational numbers does not have the least upper bound property, and this least upper bound property plays an important role in analysis. So it's better to work with a number system which has this property, and unfortunately, since Q does not have this property, that's the reason why we introduce the set of real numbers which will then have this property. So that's the goal now, to learn about the real numbers. And incidentally, from the point of view of analysis, a related thing is that not all Cauchy sequences in Q converge with a limit which is a rational number, and that we had seen when we discussed equivalence relations. It was one of the exercises. But now when we construct the set of real numbers, not only will R have the least upper bound property, but also all Cauchy sequences in R will converge with a limit in R. So to do analysis, it is convenient to work with a number system such that it has the least upper bound property and is such that every Cauchy sequence in this number system is convergent with limit again in the same number system. And this is useful because we have already seen that convergent sequences are Cauchy sequences. So this set is contained in this set. And now if this fact is true, then we will also have that the set of Cauchy sequences is contained in the set of convergent sequences, so that these two sets are in fact coincident. And this is useful to show existence results, because to check that a sequence is convergent using the definition, we need prior knowledge of the limit, whereas to check that a sequence is Cauchy using the definition, We just need to look at the terms of the sequence itself. And so showing membership in this set is easier than showing membership in this set, because we need to do some guesswork, right? And so this is a useful thing to have for a number system, because then showing existence results in analysis in mathematics becomes somewhat easier. Okay, so for that reason, there is interest in analysis to have a number system which has this property. And now we'll learn about the real number system, which indeed has the least upper bound property and is such that every Cauchy sequence in R is convergent again with a limit in R. Okay, so we'll now learn about the real number system, and to keep the notation light, for the elements of the set of rational numbers, we'll use letters like R, S, T and so on, so no boldface and just these simple letters. So before we give the formal construction of the set of real numbers, it's good to keep an intuitive idea in mind. So roughly speaking, R is going to be the set of all numbers to which the Cauchy sequences in Q want to converge to. So the idea is that given any Cauchy sequence Rn in Q, we think of this Cauchy sequence as describing a real number x. So associated with this Cauchy sequence is a real number x, and x is, in quotes, the limit as n tends to infinity of this Rn. But of course, two Cauchy sequences may have the same limit. For example, suppose that Rn is a Cauchy sequence in Q. If we perturb this Rn by a Cauchy sequence whose limit is 0, for example 1 by n, then it can be shown that this is also a Cauchy sequence, and the limit of this Cauchy sequence intuitively must be the same as the limit of this one, because the limit as n tends to infinity of 1 by n is equal to 0. Right? So if you think of this Cauchy sequence as describing a real number x, then that same x should also be associated with this Cauchy sequence. And we can keep playing this game. I can perturb this Rn by any Cauchy sequence whose limit is equal to 0, and for the purposes of talking of this real number x, all of these Cauchy sequences are then the same, because each of them has the same limit x. So this makes us suspect that perhaps there is an equivalence relation on the set of all Cauchy sequences in Q, such that under that equivalence relation, all of these Cauchy sequences belong to the same equivalence class, and that equivalence class is then the real number x. So all this is wishful thinking. So the first question is, how should we define this equivalence relation on the set of all Cauchy sequences in Q? We can define it in this way. If you have two Cauchy sequences Rn and Sn in Q, then we say that they are equivalent if the limit as n tends to infinity of Rn minus Sn is equal to 0. Okay, and this makes sense because Rn is really Sn plus Rn minus Sn, and since the limit of Rn minus Sn is 0, this would have the same limit as whatever the limit of this is, and so they should describe the same real number. Okay, so this is going to be our definition of the relation on the set of all Cauchy sequences in Q, and then the set of all real numbers is going to be the set of all equivalence classes that you get under this equivalence relation. So now we turn to the formal construction of R, having discussed intuitively how it's going to be done. So we will now begin with the formal construction of the real numbers. So we'll first give the following precise definitions. So first of all, a sequence of rational numbers Rn in Q is said to be a Cauchy sequence in Q if the following happens. For every rational number epsilon positive, there exists a capital N, such that for every little n and m which is bigger than this capital N, the distance between the corresponding terms is less than epsilon. So once again, for every rational epsilon positive, there exists an index capital N, such that beyond that index, you have that the mutual distance between the terms, which is given by mod of Rn minus Rm, is less than epsilon. Now, so far in our definitions of analysis with the epsilon delta definitions, the epsilon was just a real number, but we are not allowed to use real numbers as yet because we have not constructed them. So we have to stick with the number system that we have at our disposal, and that's only the set of rational numbers. So that's why we insist that this distance level is a rational number. The next definition is what it means for a sequence of rational numbers to converge in Q. Now, first of all, the limit of this sequence should be itself a rational number. So let R be a rational number, so this will serve as the limit, and then a sequence of rational numbers Rn in Q is said to converge in Q to this rational number R if for every rational number epsilon positive there exists an index capital N such that beyond that index the distance of the nth term to the limit is less than epsilon. So once again, for every epsilon positive, and this epsilon should be a rational number, there exists a capital N such that for every little n which is bigger than this capital N, the mod of Rn minus R is less than epsilon. Now the set of all Cauchy sequences in Q we will denote by this symbol, calligraphic C. So here is the definition of the relation tilde on the set of all Cauchy sequences in Q. So suppose that Rn and Sn are two Cauchy sequences in Q, so they belong to this set. Then we say that Rn is equivalent to Sn if the sequence with the nth term Rn minus Sn converges to 0 in Q. Let us consider a simple example, namely that of a constant sequence in Q. So suppose that R is a rational number, and let us consider the constant sequence, all of whose terms are equal to R. Our first claim is that this is a Cauchy sequence in Q. So we have to show that given any rational distance epsilon positive, there exists an index such that if I take any little n and m beyond that index, the distance between the nth term and the mth term is smaller than epsilon. So let us suppose that you have a rational epsilon positive, and let's take this capital N equal to 1. Then for every little n and m which is bigger than this capital N, you have that the distance between the nth term and the mth term is, well, each of these terms is equal to R. So this is just the mod of R minus R. R minus R is 0, so it's mod 0, which is equal to 0, and that's of course less than epsilon because epsilon was positive. So it follows that this is a Cauchy sequence in Q. In other words, it belongs to this set, calligraphic C. Moreover, let's also show that this constant sequence converges to R in Q. First of all, the limit is a rational number, and given any rational epsilon positive, let's again take this index capital N equal to 1, and then for every little n which is beyond this index capital N, you have that the distance between the nth term and the claimed limit R is given by, well, the nth term is R, so this is just mod R minus R, which is again 0, and that's less than epsilon. We will now show the theorem that this relation that we just introduced on the set of all Cauchy sequences in Q, this relation is an equivalence relation. So we want to check that this relation has the properties of reflexivity, symmetry, and transitivity. Let's begin with reflexivity. So then we have to show that each element in the set is related to itself. Well, this set is the set of all Cauchy sequences in Q. So let Rn be a Cauchy sequence in Q. And we want to show that this element is related to itself under this relation. Two sequences are said to be related to each other if, when I take the term-wise difference of these two sequences, that sequence is convergent in Q with limit 0. Okay? But if I take the term-wise difference of this sequence with itself, then the nth term is given by Rn minus Rn, so that's 0. So you get the constant sequence 0, 0, 0, and since 0 is a rational number, we know that this is convergent to 0 in Q. So it follows that this sequence is related to itself, and so we have reflexivity for this relation. So let us now check that the relation is symmetric. So suppose that you have two sequences which are Cauchy sequences in Q, Rn and Sn, such that Rn is related to Sn, but then we want to show that Sn is related to Rn as well. Okay, but first of all, since Rn is related to Sn, then we know that the sequence whose nth term is Rn minus Sn is convergent in Q to 0. So this means that given any rational epsilon positive, there exists an index capital N such that for every little n beyond this capital N, you have that the distance of the nth term of the sequence, which is Rn minus Sn, to the limit, which is 0, is less than epsilon. But this is just mod of Rn minus Sn, which is also equal to the mod of minus of Rn minus Sn, because the mod of any number is the same as the mod of the minus of that number. And minus of Rn minus Sn is Sn minus Rn. And so you have that this distance is the same as the distance of Sn minus Rn to 0. But then you have that for every rational epsilon positive, there exists an index such that beyond that index the distance of Sn minus Rn to 0 is less than epsilon. In other words, the sequence Sn minus Rn is convergent in Q with limit 0. But that's the same as saying that Sn is related to Rn. So whenever Rn is related to Sn, also Sn is related to Rn, and so the relation is symmetric. So now let us show that the relation is also transitive. So suppose that you have three Cauchy sequences in Q, Rn, Sn and Tn, such that Rn is related to Sn and Sn is related to Tn, and then we want to show that Rn is related to Tn. Now since Rn is related to Sn, we already know that this sequence Rn minus Sn converges in Q to 0. And similarly, since Sn is related to Tn, we also know that this sequence Sn minus Tn converges in Q to 0. Now we want to show that Rn is related to Tn, in other words the sequence whose nth term is Rn minus Tn, that converges in Q to 0. So let epsilon positive be any rational number, and then we know that half multiplied by epsilon is also a rational number which is positive, and by virtue of this sequence converging to 0 in Q, we know that there exists an index capital N1 such that beyond that index the distance of the nth term, which is Rn minus Sn, to the limit, which is 0, is less than half epsilon. Similarly, since this sequence converges to 0 in Q, we know that there exists an index N2 such that beyond that index the distance of the nth term to 0 is less than epsilon by 2. Now let us take this capital N to be equal to N1 plus N2, and then for any little n which is bigger than capital N, we will have in particular that this little n is bigger than N1 so that this holds, and this little n will also be bigger than N2 so that this also holds. And now the distance of the nth term to the limit for this little n beyond this capital N is given by, now I know stuff about Rn minus Sn and Sn minus Tn, but here there is no Sn, so we artificially introduced that by adding and subtracting Sn. So this is equal to mod of Rn minus Sn plus Sn minus Tn, and by the triangle inequality this is less than or equal to mod of Rn minus Sn plus mod of Sn minus Tn. But since this n is bigger than capital N, it's in particular bigger than N1 so that this holds, so this thing is less than epsilon by 2, and also this little n is also bigger than N2 so that this holds, and so this is less than epsilon by 2. But if I take epsilon as a common factor, I get half plus half, which is 1, and 1 times epsilon is equal to epsilon. So given any epsilon which is rational and positive, there exists an index capital N such that beyond that index the distance of the nth term of this sequence to the claimed limit, which is 0, is less than epsilon, and so we have proved that this sequence converges to 0 in Q, which is the same as saying that Rn is related to Tn. So if Rn is related to Sn and Sn is related to Tn, then we have managed to show that Rn is related to Tn. So we have shown transitivity. So since our relation is reflexive, symmetric and transitive, it follows that it's an equivalence relation. On the set C of all Cauchy sequences in Q, we have introduced a relation tilde, and we have just verified that this relation is an equivalence relation. Now that it's an equivalence relation, we can look at the equivalence class of any member of this set. So any Cauchy sequence in Q, you can look at its corresponding equivalence class, and the collection of all these equivalence classes that you get is the set of all real numbers. Okay, so intuitively a real number is associated with any Cauchy sequence in Q. Say R1, R2, R3 is a Cauchy sequence in Q, then we associate with it a real number x, and that's thought of as the limit that this Cauchy sequence wants to converge to. But then we had said that, well, there might be another Cauchy sequence which also converges to the same limit, in the sense that if you look at the term-wise difference of these two sequences, that converges to 0. Okay, so the real number is to be thought of as an equivalence class where each member in that equivalence class, which is a Cauchy sequence, is such that these are related to each other, in the sense that if you take any two Cauchy sequences in this equivalence class and take that term-wise difference, then that converges to 0. So this is just a schematic diagram. It has no meaning except to help us formulate this abstract thought. And similarly, if you have another equivalence class, that's a bunch of Cauchy sequences all of which are such that they are related to each other under this relation. So if I take the term-wise difference of any two members of this equivalence class, then that also converges to 0. Now we want to view every rational number as a real number. So we want a sort of pair of glasses which allow us to view any rational number as a real number. Now a real number is really an equivalence class of Cauchy sequences in Q. So we should associate with any rational number a Cauchy sequence, and our intuitive understanding is that this Cauchy sequence should be such that whatever it wants to converge to, that's the real number. Well, if the real number in question is a rational number, can we think of a sequence whose limit is that R? Of course we can, namely the constant sequence. That's a sequence in Q, and the constant sequence is a Cauchy sequence, and it is in fact convergent with limit R. And so associated with this rational number R, we take the real number, which is the equivalence class containing the Cauchy sequence in Q, which is the constant sequence R, 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 and so on. Let us check that this map, which sends R to this equivalence class containing the constant Cauchy sequence in Q, R, 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 that map from Q to R is injective. Suppose that R and S are two rational numbers such that the images under this map are the same. So that means that the equivalence class containing this constant sequence R, R, R is the same as the equivalence class containing this constant sequence SSS. But whenever two equivalence classes are coincident, if I take any element from the first equivalence class and any element from the second equivalence class, then they are related to each other. So we know that this sequence, the constant sequence R, is related to the constant sequence S. But that by definition means that R minus S converges to 0 in Q. But this is the constant sequence R minus S, R minus S, R minus S, and so on, which of course converges to R minus S in Q. But it can be shown that any sequence which is convergent in Q has a unique limit. So this is actually one of the homework exercises that you'll soon do. So by the uniqueness of limits, since we know that this constant sequence R minus S converges to both 0 as well as R minus S, this R minus S has got to be equal to 0. In other words, R is equal to S. So we took two rational numbers and we assumed that their images are the same under this map. And now we have shown that the two rational numbers must then be coincident. In other words, this map is injective. Okay, so the next task at hand is to define the addition and multiplication of real numbers. Now intuitively this will be done as follows. Suppose you have two real numbers, x and y. Now this x is associated with some Cauchy sequence in Q, and this y is associated with some Cauchy sequence in Q. Now if I term-wise add these two Cauchy sequences, then I get a new Cauchy sequence, and intuitively the x and y were the limits of these two Cauchy sequences, and then we know that the limit of their term-wise sum ought to be the sum of the limit, so that ought to be x plus y. Okay, so addition will be defined in this manner, that if you have two real numbers, you take any two Cauchy sequences in these equivalence classes, you term-wise add them, you get a new Cauchy sequence, and you then take the equivalence class of that, and that will be the sum of this x and y. And likewise with multiplication, you just take the term-wise product and do the same thing. Now to show that the product of two Cauchy sequences is also a Cauchy sequence, we will need the following lemma, which says that every Cauchy sequence in Q is bounded. And by a bounded rational sequence, we mean that there exists a rational bound M, which is a positive number, such that the mod of each term of this rational sequence is less than or equal to M. So now let's show that every Cauchy sequence in Q is bounded. So let Rn be a Cauchy sequence in Q, and let epsilon be equal to 1, which is a rational number and it's positive. So then, since this sequence is a Cauchy sequence in Q, there exists a corresponding index capital N, such that for every little n and m which is bigger than this capital N, the distance between the nth term and the mth term is less than epsilon, which was chosen to be equal to 1. So in particular, if I take m equal to capital N plus 1, then you have that for every little n bigger than capital N, mod of Rn minus Rm, which has been chosen to be capital N plus 1, is less than epsilon, which was equal to 1. So this means that Rn itself can't be too large. Indeed, we can show this using the triangle inequality, because for every little n bigger than capital N, the mod of Rn, now I know something about mod of Rn minus Rn plus 1, which is not there here. So we artificially introduce that by adding and subtracting this R capital N plus 1, and that is less than or equal to the mod of the first term plus the mod of the second term. And this we know, since n is strictly bigger than capital N, is less than 1. So this is less than 1 plus mod Rn plus 1. So we have that for every little n strictly bigger than capital N, so n equal to capital N plus 1, n plus 2, n plus 3, and so on, you have that the mod of Rn is less than or equal to this fixed number, okay, which is a rational number, and it's also positive. But also what's left out in this list are just the first capital N numbers. So for every n equal to 1, 2, 3 up till capital N, we of course have that the mod of Rn is less than or equal to the maximum of mod R1 up till mod R capital N. So now if I, for example, add these two or take the maximum of these two, that will be some big rational number such that for every little n, you have that mod Rn is less than or equal to that bound. So we take as our capital M the maximum of mod R1 up till R capital N, and then 1 plus mod Rn plus 1. So this is some big number which is a positive number and it's a rational number, and so we have that for every little n, mod Rn is less than or equal to m. And this shows that every Cauchy sequence in Q is bounded. So the lemma that we just showed enables us to show that if you have two Cauchy sequences in Q, Rn and Sn, and I take their term-wise product, then that's again a Cauchy sequence in Q. Now this is a homework exercise, but let's see a sketch of the proof, and let's also show that the term-wise sum of two Cauchy sequences in Q is a Cauchy sequence in Q. Okay, so here is the sketch of that. If I look at the distance between the nth term of the sequence and the mth term of the sequence, that's this thing. And let us combine these two and use the triangle inequality. So by the triangle inequality, this is less than or equal to the mod of Rn minus Rm plus the mod of Sn minus Sm. Now I know that if I go far enough in the sequence, then this can be made small. And if I go far enough in the sequence, also this can be made small. So their sum can also be made small if we go far enough in the sequence. And that's essentially why the term-wise sum of two Cauchy sequences in Q is also Cauchy sequence in Q. And let's also outline the proof of how one shows that the term-wise product of two Cauchy sequences in Q is a Cauchy sequence in Q. First of all, if these two are Cauchy sequences in Q, by the lemma that we just showed, both of these are bounded and they have some rational bound. So suppose that A is the rational bound of Rn and B is the rational bound for this sequence Sn. Okay, so let's look at the distance between the nth term of the sequence and the mth term of the sequence. So that's the mod of Rn_Sn minus Rm_Sm, and let's add and subtract this term Rm_Sm and Rm_Sn. So in this first thing, Sn is a common factor, and in the second thing, Rm is a common factor. So if we use the triangle inequality, this is less than or equal to the mod of this first thing plus the mod of the second thing. Now the mod of the first thing itself splits into the mod of Sn times the mod of Rn minus Rm, and the mod of the second thing splits into mod Rm times mod Sn minus Sm. But we know that mod of Sn is less than or equal to B, and mod of Rm is less than or equal to this fixed number A. And we know that this can be made small if we go far enough in the sequence, and in particular it can be made smaller than epsilon by 2b, where epsilon positive is a rational number given at the outset. And similarly, this can be made small if we go far enough in the sequence. So for example, it can be made smaller than epsilon by 2a. And so we have that this thing can be made smaller than epsilon if we go far enough in the sequence. So this is just the outline, but in the homework you will have to expand this and write out the argument carefully. Okay, so now we are ready to give the definition of how addition and multiplication of two real numbers is defined. So suppose that you have two real numbers, x and y, and let x be the equivalence class containing a Cauchy sequence in Q, which is Rn, and let Y be the equivalence class of a Cauchy sequence in Q, which is this Sn. Then we define the sum of these two real numbers to be the real number, which is the equivalence class containing the Cauchy sequence in Q, whose nth term is given by Rn plus Sn, which is the term-wise sum of these. And x times y is the real number, which is the equivalence class containing the Cauchy sequence in Q, whose nth term is given by the term-wise product of these two, which is Rn Sn. And the first task at hand is to show that these operations are well defined, that is, it does not depend on which Cauchy sequence you choose in this whole equivalence class and which Cauchy sequence is chosen from this equivalence class. Let's just see the proof of well-definedness of multiplication. So we'll now show the well-definedness of real number multiplication. Let x and y be two real numbers. Let x be the equivalence class of a Cauchy sequence in Q, namely Rn, and let us suppose that Rn prime is another Cauchy sequence in Q which belongs to the same equivalence class. And similarly, let y be another real number which is the equivalence class of a Cauchy sequence in Q. Let's call it Sn, and let's suppose that Sn prime is another Cauchy sequence in Q which belongs to the same equivalence class. Now, since Rn is related to Rn prime, we know that the sequence Rn minus Rn prime converges in Q to 0. And similarly, since Sn is related to Sn prime, we know that the sequence Sn minus Sn prime converges in Q to 0. And what we want to show is that if we use these two representatives from these equivalence classes to calculate the product, so we take their term-wise product Rn Sn and then take the equivalence class of that, then the real number that we get in this manner is the same as the real number one obtains if we use these representatives. So we take the term-wise product of Rn prime and Sn prime and then take the equivalence class of that. And what we want to show is that the then obtained real number is the same as the one that we obtained earlier with the other representatives. So we want to show that Rn Sn is related to Rn prime Sn prime. In other words, the sequence Rn Sn minus Rn prime Sn prime converges to 0 in Q. Before we give the formal proof, let us make a plan and do some rough work. So we look at the distance of the nth term to 0, which is given by the mod of this thing. And let's add and subtract this term so that we have Rn Sn minus Rn prime Sn plus Rn prime Sn minus Rn prime Sn prime and the mod of that. Now we see that in this Sn is a common factor and in these two Rn prime is a common factor. So if we use the triangle inequality on this, then this is less than or equal to the mod of the first thing, which itself splits into two parts, the mod of Rn minus Rn prime times the mod of Sn, and then the mod of the second part, where Rn prime being a common factor, it splits into mod Rn prime times mod of Sn minus Sn prime. And we know that since Sn is a Cauchy sequence in Q, we know that it's bounded with some bound, let's call it B. And we also know that Rn prime is a Cauchy sequence in Q, so that's also a bounded sequence with some rational bound A prime. Then we know that this can be made small by virtue of the fact that Rn minus Rn prime converges to 0 in Q. So this can be made as small as I please, provided we go far enough in the sequence. And likewise, this can also be made small because Sn minus Sn prime converges to 0. And so this overall thing can be made small, and so this can be made small. So that's the idea. And now let us write it down carefully. Let epsilon be a positive rational number, and since the sequence Rn prime is a Cauchy sequence in Q, we know that it has a rational bound, let's call it A prime, so that's a positive number, such that the mod of each Rn prime is less than or equal to A prime. And similarly, since Sn is a Cauchy sequence in Q, that's also bounded, and so there exists a rational bound B, which is a positive number, such that mod Sn is less than or equal to B for all indices n. Since Rn minus Rn prime converges in Q to 0, given this rational epsilon by 2b, there exists a corresponding index n1, such that beyond this n1, the distance of the nth term to 0, which is this thing, is less than epsilon by 2b. And since Sn minus Sn prime converges to 0 in Q, we also know that there exists an index n2 such that beyond that index, the distance of the nth term to 0, which is this thing, is less than this rational epsilon divided by 2a prime. So now let us take capital N to be equal to n1 plus n2, and for every little n which is bigger than this capital N, in particular n is bigger than n1 so that this holds, and in particular n is bigger than n2 so that this as well holds. So now if we look at the distance of this nth term to 0, which is this quantity, that is, we do the same manipulation as before, that is equal to this, which is less than or equal to this, and now we know that Sn is less than b because that's the bound on Sn, and Rn prime is less than or equal to a prime because of this thing, and we also know that this is less than epsilon by 2b because of this, and this is less than epsilon by 2a prime because of this one. And so overall we get this quantity which is equal to epsilon because the a prime cancels, the b cancels, and I'm left with epsilon by 2 plus epsilon by 2, which is equal to epsilon. So given any epsilon positive, we have managed to produce an index such that beyond that index, the distance of the nth term of this sequence to 0 is smaller than epsilon. So this sequence converges to 0 in Q. So that means that Rn is related to Rn prime Sn prime, and so their equivalence classes are the same. And so multiplication is well defined. So let's look at some examples. We will introduce the identity element with respect to addition and the identity element with respect to multiplication. So first consider the constant sequence, all of whose terms are 0. So that's a Cauchy sequence in Q. And let's take the corresponding equivalence class, which we denote by this symbol, boldface 0, and that we will show is the additive identity for real number addition. So for all real numbers x, we will show that 0 plus x is equal to x, and then by commutativity that will also be equal to x plus 0. If x is a real number, let us suppose that it's the equivalence class of this sequence, which is a Cauchy sequence in Q. So now let's find out what is 0 plus x. Well, we first have to take the term-wise sum of these two. That's the sequence whose nth term is 0 plus Rn, and then you have to take the equivalence class of that. So that just is the equivalence class of Rn itself, and that we know is equal to x. And it turns out that addition of real numbers is also commutative. So the moment 0 plus x is equal to x, we also know that x plus 0 is equal to x. Okay, so this 0 serves as the additive identity. Now let us introduce this multiplicative identity. So we take the constant sequence, all of whose terms are equal to 1. That's a Cauchy sequence in Q. We can take the corresponding equivalence class, and that we denote by this boldface 1. And let's show that this is the multiplicative identity. So we'll show that for every real number x, 1 times x is equal to x, and that's also equal to x times 1. Now this last thing follows from commutativity of multiplication, which can be shown, but let's show that 1 times x is equal to x. Now this, by definition, we have to take the term-wise product of these two. So that's 1 times Rn, and then we have to take the equivalence class of that new Cauchy sequence in Q. Now 1 times Rn is just Rn, and so we get back x again, and so 1 times x is equal to x. With these operations of addition and multiplication, the set of real numbers forms a field. So what does this mean? That's a succinct way of saying that the operations of addition and multiplication have the following properties, which are listed here. With respect to addition, the operation is associative. There exists an additive identity. For each real number, there exists a corresponding additive inverse, and the operation is commutative. So let's spell out these rules. Associativity means that for every three real numbers x, y, and z, you have that x plus y plus z is the same as x plus y plus z. Additive identity means that there exists a special element, which is the zero real number, which we just introduced, such that for every real number x, x plus 0 is equal to x, and that's also equal to 0 plus x. Then every real number has a corresponding additive inverse. So this means that for every x in R, there exists a corresponding real number, which we denote by minus x, such that when added to x, you get the additive identity 0, and that's also equal to minus x plus x. Now the minus x in question, if x is given by the equivalence class containing a Cauchy sequence in Q, say Rn, then we can define minus x to be the equivalence class of the Cauchy sequence in Q, which is minus Rn. So you simply take the term-wise negative of this Cauchy sequence, and that's also a Cauchy sequence in Q, and you take the equivalence class of that, and then it's easy to see that when you add minus x to x, you get the zero element. And addition is also commutative, which means that for any two real numbers x and y, x plus y is equal to y plus x. So with multiplication, we have the following properties. First of all, it's associative. So for any three real numbers x, y, and z, we have that x times the product of y and z is equal to the product of x and y multiplied by z. Then there exists a multiplicative identity, which we have just introduced, and that's this real number 1, which is such that for every real number x, you have that 1 times x is equal to x, which is also equal to x times 1. And every non-zero real number has a multiplicative inverse. So that we will soon show, and that says that if x is a non-zero real number, then there exists another real number which we denote by x inverse, such that x times x inverse is the multiplicative identity, and that's also equal to x inverse times x. And moreover, multiplication is commutative. So for every two real numbers x and y, x times y is equal to y times x. Then there is this extra property which combines these two operations, and this property says that multiplication distributes over addition. So for any three real numbers x, y, and z, x times y plus z is equal to x times y plus x times z. So multiplication distributes over this addition. So we'll soon prove the existence of multiplicative inverses for non-zero real numbers, but all the rest of the properties can be shown in a straightforward manner using the definition of addition and multiplication of real numbers. Now we also remark that if you look at the set of rational numbers with its operations of addition and multiplication, then that also has the structure of a field. So all of these properties hold for the rational numbers with its operations of addition and multiplication. However, if we look at the set of integers with its operations of addition and multiplication, then that does not have the structure of a field. The addition and multiplication have all of these properties except for the existence of multiplicative inverses for non-zero integers. Indeed, we have seen, for example, if you look at the equation 2x is equal to 1, then there is no integer solution x. So the integer 2, which is a non-zero integer, does not possess a multiplicative inverse. Okay. Now a structure where everything holds except multiplicative inverses are not guaranteed to exist, that structure is called a ring. And so the set of integers with its operations of addition and multiplication is not a field, but rather it forms a ring. And in chapter 5, we will study this ring theoretic structure of the set of integers. To show that every non-zero real number has a multiplicative inverse, we will need the following technical lemma, and this says the following. So suppose that x is a non-zero real number. So this is really an equivalence class which contains Cauchy sequences in Q, and suppose that Rn is one such Cauchy sequence, that is, this Cauchy sequence belongs to x. Then there exists a corresponding rational number d positive, and there exists an index capital N, such that when I take any little n beyond this index capital N, the mod of Rn is bigger than d. So roughly speaking, the Rn's are bounded away from 0 through a positive distance d, which is a rational number. So pictorially this means the following. Here is the positive rational number, and here is the index capital N, and then all the terms of the sequence beyond this n, they lie in this shaded portion. So they are away from 0 through a distance of d. Okay, so let's prove this. We know that x is not equal to 0, and since Rn belongs to x, we know that x is the equivalence class containing this Rn. And 0, recall, is the equivalence class containing the constant sequence with all terms equal to 0. So we know that this equivalence class is not equal to this equivalence class. In other words, it's not the case that Rn is related to 0. So it's not the case that Rn minus 0 converges in Q to 0. Let's first see what it means for this sequence to converge to 0. It means that for every rational epsilon positive, there exists a corresponding index capital N, such that for all little n beyond this capital N, the distance of the nth term, which is Rn minus 0 to the limit 0, is smaller than epsilon. So since it's the case that this does not happen, this means that it is not the case that for every rational epsilon positive, there exists a capital N such that beyond that n, mod of Rn is less than epsilon. So this means that there exists a bad rational epsilon which is positive, which prevents this from happening. In other words, for every capital N in n, this does not happen. In other words, there exists a bad little n which is bigger than this capital N such that this does not happen. In other words, mod of Rn is bigger than or equal to epsilon. So once again, the fact that it is not the case that this happens is the same as saying that there exists a rational epsilon positive such that for every capital N in the set of natural numbers, there exists a little n which is bigger than this capital N, but mod of Rn is bigger than or equal to epsilon. And this highlighted portion of the sentence, let's label that as star because we'll soon use that. Now we know that this Rn is a Cauchy sequence in Q, and so for this rational epsilon positive, we know that half epsilon is also a rational number which is positive, and so there exists a corresponding index, let's call it capital N star, such that for every little n and m which is bigger than this capital N star, we have that the mutual distance of the terms is less than epsilon by 2. Now, in this highlighted statement, for every capital N we take, there exists a corresponding little n such that blah 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 happens. So, if we take this capital N equal to capital N star, then there exists a corresponding index, let's call it little n star, which is bigger than this capital N star, such that the mod of Rn star is bigger than or equal to epsilon. So now we claim that this n star is this index that we are seeking, and then for every little n which is bigger than this capital N star, we have that the mod of Rn, which is equal to mod of Rn minus Rn star plus Rn star, so I simply add and subtract this term, and now we'll use the reverse triangle inequality. So think of this as the A and this as minus B. Then we know from the reverse triangle inequality that mod of A minus B is bigger than or equal to mod of mod A minus mod B, and that's furthermore bigger than or equal to the thing without the mod sign, so mod A minus mod B. Now A is Rn star, so you just get mod Rn star, and mod of this minus B is the same as the mod of B, and so you can just put mod of Rn minus Rn star. So we have this thing, and what do we know? We know that mod of Rn star is bigger than or equal to epsilon, and on the other hand, from over here, whenever I have two indices which are bigger than n star, you have that the mutual distance is less than epsilon by 2. Now this little n star is bigger than this capital N star, as well as we are taking this n which is bigger than capital N star, and so this mutual distance is less than epsilon by 2. So the minus of that will be bigger than minus epsilon by 2. So you get epsilon minus epsilon by 2, which is epsilon by 2, which is a rational number. Let's call it D. So what we have managed to show is that here is an index such that for every little n beyond this index, the mod of Rn is strictly bigger than this rational number D, and so we have exactly proved the statement of this lemma. Okay, so this was a technical lemma, but now we have got what we wanted in order to prove that every non-zero rational number has a multiplicative inverse, which we'll now do. Okay, so we are now ready to prove the theorem that every non-zero real number x has a multiplicative inverse. So there exists another real number which we denote by x inverse, such that when multiplied to x, you get the identity element, and then since x times x inverse is 1, also x inverse times x is 1 by commutativity. Okay, so let's prove this. We know that x is a non-zero real number, and let us suppose that Rn is a Cauchy sequence in Q which belongs to this equivalence class. Then by the lemma that we have just learned, there exists a rational number D which is positive, and there exists an index capital N such that for every little n beyond this capital N, you have that the mod of Rn is bigger than D. And this D is positive, so we immediately know that then Rn can't be 0. Now let us define Sn to be equal to Rn inverse for n bigger than capital N, because there Rn is not equal to 0, so Rn inverse exists as a rational number. And for little n in between 1 and capital N, you can define it what you like. So let's, for concreteness, suppose that this Sn is equal to 0 for all these n's. So let's note that Sn is a rational number for each n, and what we are soon going to do is we are going to show that this Sn is actually a Cauchy sequence in Q, and then when we take the corresponding equivalence class containing this Cauchy sequence and call that x inverse, then that's the real number which does this job. Okay, so let's first observe that when little n and m are bigger than capital N, so that then Sn is given by this formula. Mod of Sn minus Sm is mod of 1 by Rn minus 1 by Rm, and if we simplify this, that turns out to be mod of Rn minus Rm divided by mod Rn times mod Rm. And we know that when n is strictly bigger than this capital N, the mod of Rn is strictly bigger than d. So 1 by mod Rn is then less than 1 by d, because of which we get that this is less than or equal to mod Rn minus Rm divided by d square, because 1 by mod Rn and 1 by mod Rm are both less than 1 by d. Okay, so then we know that if we go far enough in the sequence, then this can be made small, so that this can also be made small. Okay, so here is the proof of the fact that this Sn is a Cauchy sequence in Q. So let epsilon be any positive number which is also rational. Then we know that since d is rational, also epsilon d square is a rational number and is of course positive. So then, because Rn is a Cauchy sequence in Q, it follows that there exists some index n prime such that for all little n and m beyond this capital N prime, you have that the mutual distance between Rn and Rm is less than epsilon d square. So now if I take this index, capital N plus capital N prime, and I take any two indices beyond this thing, then the mod of Sn minus Sm, well, in particular n and m are bigger than this capital N, so that this estimate holds, right? And so this is less than or equal to mod Rn minus Rm by d square, and moreover, since little n and m are also bigger than this capital N prime, also this estimate holds, so that the numerator is less than epsilon d square, and then in the denominator we have d square. The d square conveniently cancels, leaving an epsilon. So we have that given any rational epsilon positive, there exists an index, namely this one, such that beyond that index, the mutual distance of the terms is less than epsilon, so that this Sn is a Cauchy sequence in Q. And so we can take the corresponding equivalence class containing this Cauchy sequence in Q, and let's call that as the real number x inverse. So it remains to show that x times x inverse is equal to 1. Now if we calculate what is Rn Sn, then we note that for little n which is bigger than this capital N, Sn is given by Rn inverse, so this turns out to be equal to 1. And for the first few, we know that Sn is equal to 0, so that this becomes 0 for little n in between 1 and capital N. So if we look at the sequence Rn Sn minus 1, then for little n beyond this capital N, this is the constant sequence 0, 0, 0, 0, 0, and so of course it converges to 0 in Q. So you have that xx inverse, which is the equivalence class containing the term-wise product of Rn and Sn, that's this sequence. That sequence is related to the constant sequence 1, 1, 1 because Rn Sn minus 1 converges to 0 in Q. And so the corresponding equivalence classes are the same, but this is the identity element with respect to multiplication. So we have managed to show that x times x inverse is equal to 1, and this shows that every non-zero real number has a multiplicative inverse. So next time what we'll do is we will define the order relation in R, and then we'll talk about the least upper bound property of R and also discuss rational and irrational numbers.